Okay, so this is lecture 4, although the slides are at lecture 3, but today's lecture will be devoted to the 2 period maps that go from, generally speaking, from deformation spaces of p-divisible groups to certain types of Grassmannians or generalized Grassmannians. And the first is the Grothendieck-Messing, or sometimes called the Ram period map. The second is the Hodge-Tate period map. And we will gradually increase our pool of deformation examples. We started with Lubin-Tate. I will start now talking about Rapoport-Zink deformation spaces, first without PEL level, and I will say something, not much, about PEL level because I will want to introduce the Drinfeld example, which is very basic. So let's start with Rapoport-Zink deformation spaces. As usually we denote by little k an algebraically closed field of characteristic P, by W its Witt vectors, and by H0 a fixed p-divisible group over K of height H and dimension D. It need not be formal now, it can be anything, and the dimension need not be 1. So the Lubin-Tate case was when the dimension was 1 and H0 was a formal, the unique formal p-divisible group of height H in dimension 1. And we let M0 be the crystal, the Grothendieck-Messing crystal of H0 evaluated at the PD thickening W goes to K. Okay, so the kernel is P times W. It has divided power structures. We can evaluate it. It's free of rank H over W. And of course, it's got Frobenius and Verschiebung acting on it. Now, the test objects in Rapoport-Zink, that's a little bit annoying, is not the same category CK that Lubin and Tate used. It's the category nilp W of all W algebras in which P is locally nilpotent. Okay, but the rings that we'll be interested in, like OC over P to the N, or limits, inverse limits of such rings, will be considered. And the deformation functor is defined very similarly. It's D of S is the set of all couples G iota, where G is a p-divisible group over S. That once you reduce mod P, once you base change to S over P, it becomes quasi-isogynous or isogynous to this H0, our example, spread all along S over P. So S over P, of course, is a K module, a K algebra. And, but you have, of course, to rigidify it by including in the data the quasi-isogeny iota. So in the case where P is not nilpotent, but only topologically nilpotent, if S is a p-adic W algebra, we let D of S be the inverse limit of D of S over P to the N with respect to the obvious maps.
Yeah.
Yep.
I guess you probably need to modify some.
Oh yeah, always up to isomorphism.
The isomorphisms respect the
G and iota. So
G and iota.
of course. Yeah.
Because the other one.
No. No, the other one respected G and iota too. Always you respect G and iota. Otherwise, there's no chance of being representable because it's not rigid. And isomorphism is what you think. It's a triangle G isomorphic to G prime, so that the maps via this isomorphism, the iota and the iota prime commute. No, but that was the case in the Lubin-Tate case as well. Yeah, for sure. No, what do we discuss? I know what you're referring to. I'll clarify it in the break. Okay. And the point to note is that since we are including iota in the data, and since the crystal is a crystal, so is uniquely determined by the reduction mod P, we have that MGS depends only on G naught, so to speak, on G reduced mod P, which is quasi-isogynous. So if you invert P and you look at the rational crystal rather than the integral crystal, you get via iota an isomorphism with M naught tensor SQ. Of course, you have to extend scalars to get a modulo over S. Now, the Lubin-Tate case, D was 1, H0 was formal, as I said. The test object came from this category of complete Noetherian local rings with residue field K. But you can relate the two categories by considering S R over MR to the N. And then in the Lubin-Tate case, we're considering for iota quasi-isogenies over the residue field. Here we're considering quasi-isogenies over S over P, and S over P is not quite the residue field, it might be bigger, but by rigidity of quasi-isogenies that we discussed, I think, in the second talk, every quasi-isogeny over the residue field has a unique lift to quasi-isogeny over S over P, so this is the same moduli problem. However, if you take rings which are not of this sort, you should be careful. For example, for the power series ring over K, formally speaking, so to speak, the two deformation problems give different answers. Sorry? No, M was my notation for the Lubin-Tate deformation functor, and D is for the Rapoport-Zink. Corresponds to a p-divisible over S. Yeah, so here, it's...
No, but over S modulo p,
Right. Of course, that's the same. A comparable family and yeah. That's tautologically the same. Now, one thing that I should warn you about is that in the Lubin-Tate case, we said that going from an isomorphism, iota being an isomorphism, to being a quasi-isogeny was only a matter of height, because if a quasi-isogeny of height 0, and I more or less proved it or explained why, is an isomorphism in the Lubin-Tate case, that's not true in general. It's in a very strong way not true in general. So even if you take a talk about quasi-isogenies of height, you cannot repeat quasi-isogeny by isomorphism. So let's look at some examples. For example, let D equal 1 and H equal 2, but let's take for H naught, not the one that's considered by Lubin-Tate, which would be the formal group of a supersingular elliptic curve, but rather just the ordinary case, QP over ZP times mu p to the infinity. Now in this case, we have shown that, or we know that mu p to the infinity and also QP over ZP, since it's étale, or if you want, since it's the dual of mu p infinity, do not deform. So the only thing that can deform is the extension class, so to speak, okay? Over a perfect field, remember, it always splits, but over a general ring S, there are interesting deformations that come from extensions. And you can compute the extensions, it's an easy exercise, and you get that it's canonically given by the formal multiplicative group. So this leads to what's called the Ghate canonical coordinates on residue disks, for example, of ordinary elliptic curves in the modular curve, or generally speaking in moduli spaces. If S equals K, you just get a point. I should say that in general, you can take here, you can take here S equals K, and then of course what you get is simply the classification of all the p-divisible groups over K that are quasi-isogynous to H0 up to isomorphism. Okay? So that's included in the special fiber of the deformation problem. As another example where the special fiber is interesting, let's take D equal 2 and H equal 4. And let's take for H0 the product of the formal group of a supersingular elliptic curve with itself. And in this case, even when S equals K, you'll get infinitely many examples because there are actually families parameterized by projective lines of pairwise non-isomorphic isogenous p-divisible groups that are all isogenous to H0. These were constructed by Moret-Bailly, and they're called Moret-Bailly families. They're constructed by sort of varying alpha p somehow in a P1 family and dividing by this alpha p. And as the last example, again, the Lubin-Tate case, H0 is as in the Lubin-Tate case, and again, the special fiber is a point. So the special fiber of the deformation problem can be a point, can be a very interesting, as we will see actually, scheme or, yeah. So the main theorem of Rapoport and Zink, or previously in some cases was proved by Greenfield, is that this functor is representable. I put it in quotation marks because the test objects came from this category nilp W, and the representing functor is formal scheme. It's only an int object in some sense, so it doesn't strictly lie in the category nilp W, but nevertheless it's representable by a formal scheme over W, whose ideal of definition is locally finally generated. Remember, a formal scheme is everywhere, locally everywhere of the form spef A, where A is an adic ring, which has an ideal of definition. So this ideal of definition is locally finally generated. And every irreducible component of the reduced special fiber is proper over K. So in the examples that we had before, either it was a point or it was something that maybe had some P1s in it. It need not be of finite type in general, but the irreducible components are proper. And we're going to construct a period map, pi Grothendieck-Messing, that will be a map of analytic spaces over W1 over P, or if you want, over spa of W1 over P W, okay, in the adic language, from the generic fiber of the adic space associated with a formal scheme D, whose existence was just mentioned here. Of course, I'm not going to prove this, to the analytic adic space associated to a certain Grassmannian, and it will be the Grassmannian of d-dimensional linear spaces in M0. M0 was h-dimensional, so it's Gra dh, but canonically it's the Grassmannian of d-dimensional quotients, rather, let's put it this way, of M0. And for simplicity, we will only describe it naively on points in OC or in C, okay, over the pair SPA COC. So we have everything prepared to describe it. We take S now OC, S over PC, S over PS is OC over P, and if we have a couple G iota in D OC, we can identify, as I said before, via iota, the crystal with the fixed model M0, and since we inverted P, tensor C. Okay, so I'm working rationally, not integrally. However, the crystal, remember, is the Lie algebra of the universal vectorial extension. It maps canonically to the Lie algebra of G. And as I mentioned, the Lie algebra of G, unlike the Lie algebra of the universal vectorial extension, is very much dependent upon G over OC, or if you fix H0 on how you lift H0 from OC over P to OC. And this lifting is only up to quasi-isogeny, remember. So this means that to such a pair, we got a quotient, a d-dimensional quotient from this h-dimensional C vector space, and this gives us the desired point in the Grassmannian over C. Okay, so the Grassmannian, as I said, is canonically the Grassmannian of d-dimensional quotients of M0. What does it want here? A double flash allow. Okay. Okay. Now, it's a fact that as an analytic map, it is in fact a transcendental map. We'll see in a moment an example. But it is an étale analytic map. That's one important fact. And the first example is actually an old computation that was done by Debargha, not so much in this language. And this is the example that we considered as the first example. D is 1, H is 2, and we want to deform QP over ZP times mu p to the infinity, and the only thing that deforms, as I said, is the extension class, and therefore you get the formal scheme that represents it is GM hat, and its OC points are the open unit disk delta around 1 in OC. And it turns out, of course, the Grassmannian of lines in the plane is just P1, and it turns out that the map, the period map in this case, simply takes Q to log Q. Now I want to stress three interesting things, very interesting things about this example. First of all, you already see from this example that the map is transcendental, analytic but transcendental. Secondly, you see that the image is not a full Grassmannian, it's only A1. Okay, the image over C of the whole unit disk is the whole A1. And the last thing, if you only restrict to the W points, okay, to deformations over the Witt vectors of FP bar, then you are in P times, right, the open unit disk, everything which is W valued is divisible by P, and there the logarithm is 1-to-1 with inverse exponential that converges. So on the W points, you get into a residue disk, and it's 1-to-1. However, if you go beyond the W points, if you go closer and closer to the boundary, you start encountering roots of unity in the kernel of the logarithm, and the map A ceases to be 1-to-1, and actually on the whole thing it's infinite to 1, and B doesn't go into one residue disk anymore, right? The logarithm only on P times, on things that are divisible by P, goes into things that are divisible by P, but when you approach the boundary of the unit disk, you get things that are fill up everything in C. So this is actually a general fact. The deformation main theorem of Grothendieck and Messing, and in fact what Grothendieck predicted in his Montreal lecture notes and Messing really proved in detail in his thesis, is that as long as you're in the unramified situation, or in general, as long as you have rings which are unramified. Yeah, let's just stick to this. The unramified case, so points in D of W, then a deformation is uniquely determined exactly by this choice of the map from the crystal evaluated at W to the Lie algebra. In other words, the only extra information that you have to give to determine a deformation is the Hodge filtration, so to speak. Now, what restriction do we have on this? Of course, it should reduce to the map to the Lie algebra of H0, and this gives us basically that in the Lubin-Tate situation, the W points map 1-to-1 into the residue disk in this projective space, reducing to the point over FP bar corresponding to H0. However, so this, you may say this is good because we knew a priori that naively, so to speak, we had the Lubin-Tate coordinates, remember U1 up to UH minus 1, and all the W deformations were classified by the maximal ideal in W to the power h minus 1 via these coordinates, and now they're classified via h minus 1 coordinates in a residue disk in pH minus 1. So you may wonder what's the relation between the two. And the relation is very complicated. That's exactly the period morphism. And if you want to see it worked out, look at the appendix to Gross and Hopkins' paper, where they do it for h equals 2, and they get formulae, and it can get very complicated. So it's typically like the log. It's one-to-one only on things that are divisible by p. So for example, if you are over the Witt vectors, anything that is the maximal ideal will be divisible by p. But as you go further and further, you lose this property of being one-to-one. And in fact, if k is already a finite ramified extension of W1 over p, OK to little k is no longer a divided power thickening. It's a nilpotent thickening, but with no divided powers because of the ramification. So the theorem of Grothendieck and Messing that I quoted here does not apply. We still have by Lubin-Tate that via the Lubin-Tate coordinates, the OK points of the deformation space are classified by mk to the h minus 1. But now what goes wrong is that a quasi-isogeny of height 0 over OK over P, in contrast to Fp bar, OK over P will have nilpotence now, right? Need not be an isomorphism. So if you look at even the height 0 component of the Rapoport-Zink space, or the Lubin-Tate space, it's the same, with ramification, you only get a quasi-isogeny, so it only induces an isomorphism between M0 tensor K, the rational M0, with the rational crystal of G. And therefore, when you take the map quotient to the Lie algebra, you only get it rationally and not integrally, so you cannot talk about the reduction. So you cannot do what we did before and say that the image lies in a residue disk. And the resulting period map is not one-to-one. In general, as I said, the image is not confined to residue disk. In fact, in the Lubin-Tate case, but not in general, we will discuss the image. If you replace K by C, it is surjective, and the fibers are infinite. And in fact, the Lubin-Tate case was studied very carefully by Gross and Hopkins, and they obtained the following result. First of all, the map is D star equivariant. Remember, D was the division algebra of invariant 1 over H, which acted on the moduli space. It also acts on pH minus 1 in the obvious way. When you extend scalars to C, D becomes matrix ring, so D star becomes GLH of C, and it acts on pH minus 1 by fractional linear transformations. Of course, there's a choice of coordinates involved, but up to a linear change. Then you may ask, and this answers Jim's question. Jim, you asked before, when are two such points isomorphic without, or quasi-isogenous without the compatibility with the iotas, okay? Just abstractly, as we discussed in the case of your question last time. And this happens if and only if they have the same Grothendieck-Messing period. So again, in the Dwork example, the kernel of the log was the roots of unity. These roots of unity, p-power roots of unity in the residue disk around 1, the open residue disk around 1, corresponded to quasi-isogenies between these extensions that did not result, that did not commute with that did not make an isomorphism on the whole diagram. Right? They were quasi-isogenies, but not isomorphic. So This is one non-trivial result, of course, in Hopkins, but perhaps the deepest result is that in this case, the period map is surjective, and point 4 is a formal consequence of 2 and 3. Remember that we enriched or enhanced the Moduli problem by considering level structure, and we got the Lubin-Tate tower. Now, the Lubin-Tate, the period morphism goes only from M to projective space, but you can consider it, of course, all the way from M infinity to projective space. And on M infinity, we had an action of GLHQP. Now, when you mod out by GLHZP, you get M eta. Okay, this simply means modding out by GLHZP simply means forgetting the p to the infinity level structure, right? But what is modding out by GLHQP? Modding out by GLHQP is more than forgetting the p to the infinity level structure. It's also allowing isogenies, right? If you think of what it means, the difference between QP and CP is also allowing isogenies. So you really forget the distinction between things that are isogenous, and this, in view of 2, means that you get exactly, the quotient is exactly this projective space. Of course, all this is done very naively here on the level of points. It should be done, and it is done correctly on the level of adic analytic spaces, which would be too difficult to do now. So these are the things that I explain now. And the question arises, what is the image of the period morphism in general? So we saw 2 examples. We saw the Lubin-Tate example where it was onto. We saw the example by Dwork where it was the logarithm and it was onto A1 into P1, so it need not be onto always. And the general notion that allows you to speak about the image of the period morphism is the notion of weak admissibility. So let me now introduce it, because we've seen similar things appear, and I think it will appear in your talks, or yeah, it will appear also in Denis' talk today or tomorrow today. So, okay, given an exact sequence, and now W, I'm sorry for using the same notation, is not the Witt vectors. This W is the subspace, sorry, is the quotient of M0, like the Lie algebra, right? So, given this h-dimensional vector space and a d-dimensional quotient, there is a kernel, which is the Hodge filtration, and I call it Phil, in honor of the Hodge filtration. And then I get an associated filtration where Phil 0 is everything, Phil 1 is this, and Phil 2 is 0. And with this, the couple N with a filtration, where N is the isocrystal, it's actually the Kroton-Messing crystal associated at OC, evaluated at OC, and then rationalized, becomes what's called an F isocrystal. And if N prime is any sub-F isocrystal, you can look at the induced filtration. Okay, in general, a sub-object in this category of F isocrystals with filtration will be another F isocrystal with filtration, and a map that respects the filtrations, but the filtration on the sub-object need not be the full intersection of the filtration on the big object with a smaller one. So when this happens, you say that it is a strict sub-object, or you just define it this way. So let's assume that N prime is a strict sub-object. And for any filtered F isocrystal, we define the Newton terminal point and the Hodge terminal point in the following way. So for the Newton terminal point, we take the Frobenius, that's part of the F isocrystal structure, and we describe it in a matrix, H by H matrix. It depends on the basis, of course, but the valuation of it is independent of the basis, because when you change the basis, you do not conjugate it, but you sigma conjugate it, right? if F was your matrix describing Frobenius, and you make a change of variable, then you change the matrix by sigma conjugation. Can you see it? It's not PF P minus 1, but it's sigma PF P minus 1. But nevertheless, the determinants of sigma P and P have the same valuation, so the valuation of the determinant is well defined, and that's T Newton. And T Hodge will simply be the dimension of the filtration. In this case, it will be D. In general, if we have a filtration of arbitrary length, not just two steps, in arbitrary breaks, then it will be given by this formula. So here only, you see it's 0 times the dimension of everything is 0 plus 1 times the dimension of field plus 2 times the dimension of GL 0 is already 0 again. And we call N weakly admissible if for any strict sub-object, so as I defined before, sub-F isocrystal endowed with a filtration induced by that of N, the endpoint of the Hodge polygon, T Hodge, let's just call it T Hodge. T Hodge of N prime is less than or equal to T Newton of N prime with equality for N prime equal N. So this reflects some general principle of Hodge polygons lying below Newton polygons. That's like a slogan that goes with all this theory and has some deep meaning, but right now it's just a definition. So given H0, the weakly admissible period domain is an open subspace F fracture, weakly admissible inside the Grassmannian, inside the analytic Grassmannian, whose C points just contain all those d-dimensional quotients, all those candidates to be the Lie algebras of liftings, for which N is weakly admissible. Okay, so once again, this was an F isocrystal. This is a quotient, a d-dimensional quotient that defines a filtration, and we want this filtration to satisfy the condition for being weakly admissible. So it's a fun exercise in linear algebra, or actually in sigma linear algebra, to make up some examples. You know how all F isocrystals look. We have classified them by the Manin-Dieudonné theorem, and you can start putting filtrations and just check what this condition gives you, and you'll see immediately that in the Lubin-Tate case, it doesn't give any restriction. In the case, for example, it's fun to work out the case where D is 2 and H is 5. You get, I think, 7 kind of possibilities for the numerology, but if we had more time, I would do one of these exercises, but it's pretty elementary, but pretty, it teaches us quite a lot. And the theorem, which is a deep theorem, we'll get back to it tomorrow as an application of the Fark-Fontaine curve, is that the image of the Grothendieck-Messing period morphism lands inside this weakly admissible open subset of the Grassmannian, analytic open subset, and contains all the classical points of it. So for a long time there was a question whether it's equal to it. So it's equal to it in the sense of closed points, but it so happens that there are Berkovich points, or as we saw yesterday in one of the talks, Gauss points, or more general points of adic spaces that are not covered. And in fact, there's a lot of work done today. I'm not an expert on this, but I think that Shen will be here next week. I saw that is one, and he might. Oh, he's not coming? Shen. anyhow, he's one of the experts on this. So maybe I thought he would speak on it. So of the two statements, the first is relatively easy, not easy, but relatively easy. But the second, that the image contains all the classical points, is the famous Commes-Fontaine theorem that weakly admissible implies admissible. Admissible by definition is everything that's in the image. Weakly admissible is everything that satisfies this criterion that we gave before. So now we get to the second, maybe that's a good point to ask for questions. So, because we finished all that I wanted to say about the Grothendieck-Messing period. So maybe I'll just round it up once again. It goes from the Rapoport-Zink in general, or Lubin-Tate in the special case that we're considering at the beginning, moduli space, to a certain Grassmannian, but it is a transcendental analytic map. It's not an algebraic map. And the image goes into, or is contained in some open set that's characterized by this weak admissibility condition that we had here on this slide. And a deep theorem says that on closed points meaning not C points, meaning points closed in the sense of a rigid analytic space or a adic space defined over W. Okay, so this means points that are defined over finite extensions of W, okay? Like in algebraic geometry, if the right is defined over Q, C points are not closed points of it, they are generic points in some sense. Okay. So now we get to the second period map, the Hodge-Tate map, and I want to recall something that was perhaps the beginning of p-adic Hodge theory 50 years ago, that appeared in Tate's paper on p-divisible groups. So recall that we had this map, alpha G, that goes from the p-adic Tate module of G to the cotangent space at the origin of the dual, omega G hat, or G dual. And this alpha G, I remind you, obtained as the restriction to TPG of the map that we called SG, that went from the universal covering, which included the Tate module, to the Grothendieck-Messing crystal. But it could be described concretely on this level, and this is how Tate actually defined it many years ago without any reference to the things that came later. So the theorem says that there is an exact sequence, and now we're over C, okay? So in general, it applied to any ring R, or any p-adic ring R, but now we're over C, so our R is OC, and we evaluate everything at OC, and then, as usual, to get a rational statement, we invert P. So the alpha G is onto, and the kernel is the image of a map that's obtained by duality from the Lie algebra of G. So we will explain this duality in the next slide, but for the moment, just concentrate on this exact sequence. The middle term is a vector space of dimension H. The quotient here, or rather this something, has dimension D with our notation. The dimension of the Lie algebra is the dimension of the p-divisible group. And the dimension of the dual p-divisible group is H minus D. So the dimensions add up correctly, at least. The second thing that goes under the name Hodge-Tate decomposition strengthens this and says that if G is defined over OK, where K is a complete discrete valuation field, okay, so a finite extension of W1 over P, then the sequence splits canonically in a way that respects the action of the Galois group, absolute Galois group of K. So you can write TPG as omega direct sum with the Lie algebra. And now it becomes really important that I put this Tate twist here over the Lie algebra, as long as I didn't consider anything but the Lie algebra is a vector space. It wasn't crucial, except for maybe this thing being defined canonical. But here, when I talk about Galois action, so the Lie algebra in this case, the Lie algebra of GC is the base change of the Lie algebra of GK. So it gets the semilinear via base change, it gets a semilinear Galois action. And this semilinear Galois action, you still twist by the cyclotomic character. So what is this map here? But before I turn the page, let me make one historical remark. Tate, in fact, did not prove part 1. Part 1, I think, was first proved by Foltings, even for p-divisible groups. And the reason is that Tate used, he only was considering p-divisible groups defined over discrete complete fields, and he used the Galois group in a very essential way, and cohomology of the Galois group, to prove the Hodge-Tate decomposition, and from the Hodge-Tate decomposition, of course, you get the existence of exact sequence. But in general, the exact sequence still exists, but does not split anymore. There's no canonical splitting, and it's very important because the failure to have a canonical splitting is what is responsible at the end for the existence of this Hodge-Tate periods. So what is the map going into the middle term? So we start with Lie G twisted once. This is the same. Lie G is the dual of omega G, so this is the same as the Holmes from omega G into the Tate module of mu p infinity because of the Tate twist, okay, canonically. And if everything was defined over K, even Galois equivariantly. So this, of course, can be sent via duality to TPG hat to the Holmes, sorry, from TPG hat tensor C to the same thing, simply because alpha G, or rather alpha G hat would send us from here to here. So a dual map would send us from the homomorphisms from here to here to homomorphisms from here to here. But this, via the Weil pairing, or the generalization of the Weil pairing for p-divisible groups, is just the p-adic Tate module of G. So the roles of G and G hat were exchanged. That's why I do not consider alpha G, but alpha G hat. I also dualize this. I take the dual of alpha of the dual group. And on top of all this, because I'm using the Weil pairing, I have to twist by 1. Now, the definitions of the two maps are straightforward. It's also not so difficult to prove that the composition is 0. But the main thing to prove here is actually that this is onto, or by duality, that this is injective. And this is what Tate did. And we will see maybe tomorrow another proof of it. And again, to get 2 from 1, Tate invoked his results that were mentioned in one of the talks before about Galois invariance and the first Galois cohomology of twists of C by the cyclotomic character. And one other remark is that in Folting's approach and in the more recent approach of Scholze, to get even a new proof of this that works even in the rigid analytic setup, not only in the algebraic setup. The Hodge-Tate map or spectral sequence is, the Hodge-Tate exact sequence is obtained from a very general Hodge-Tate spectral sequence that applies in many, or actually in any other situation known to us today, and not only in the case of abelian varieties or p-divisible groups. So this is the beginning of a big theory. So what is the Hodge-Tate period map? Consider now not just G and iota, but G and iota with a full p to the infinity level structure. Okay? So you want to trivialize all the p to the n torsion points on your formal group for all n. So this is an element not, in the Lubin-Tate case, not of the deformation space alone, but of the space at the top of the tower that we described 2 days ago by a result of Weinstein. You can use alpha infinity, this level structure, to identify the Tate module with zb to the h. And of course, you can tensor this with C to get an identification of the Tate module tensored with C as a vector space over C with C to the H. And then this map alpha G, which goes onto omega G hat, gives you a quotient, which in our case will be an H minus one dimensional quotient. Remember, in our case, G was one dimensional, its Cartier dual was H minus one dimensional. So the kernel is a line, and you map this triple G iota and alpha infinity to this line. So you get a line in P in C to the H, in other words, a point in PH minus one of C. And this is the Hodge-Tate map on the level of C points. And two remarks that unlike the Grothendieck-Messing period map, the Hodge-Tate map is defined only at the top of the tower. Okay, you really need the trivialization to define it. And it goes canonically into pH minus 1 of C. Okay, into a Grassmannian, which is pH minus 1, while the Grothendieck-Messing period map landed in the Grassmannian of all lines in M naught, which was also pH minus 1, but only once you fixed coordinates on your M naught. So there are subtle differences, and the two things, of course, should not be confused with each other. And the fact that I will not have time to discuss is that what we described here at the level of C points, points in CP or OCP rather, comes in fact from a rigid analytic or an adic analytic map between the generic fiber of the adic space associated with the Lubin-Tate tower at infinity, the one that we discussed when I was describing this result by Weinstein, to the adic space associated to pH minus 1. And in our case, we're only considering the Lubin-Tate case, again, like the Grothendieck-Messing map, it is et al. It commutes with the action of D, of the multiplicative group of D on the moduli space, because it doesn't really use iota, okay? Out of G iota and alpha infinity, it only uses G and alpha infinity. There's no mention to iota, and delta only changes such a triple by acting on the iota. So it really is invariant under composition with delta, and it intertwines the actions of GLH, the other group that acts on the moduli space at infinity via change of level structure and p to the h minus 1, and that's obvious, right? That's just linear algebra, because that action only changes alpha infinity by precomposing with the linear change of variables here, and this will result, of course, in a fractional linear transformation on the projective space side. So let me now connect it to what Debargha was doing yesterday and what other people might be talking about to the global picture. But this only in the case where H is 2. So when H is 2, H0 is the, as I said several times, the formal group of a supersingular elliptic curve. So you can think of the deformation via the Ghate theorem, you can think of the deformation space of this formal group, which is a one-dimensional open disk now, as sitting in the modular curve as a rigid analytic open disk, as a residue disk of this supersingular elliptic curve. Of course, in the modular curve, you also add some other information that's irrelevant to us here, which is tame level at some capital N that has nothing to do with P. So there could be many residue disks like this that depend on tame level, but let's focus on one of them. And let's start now to go up the p to the infinity level tower. Okay, so we add full p level, full p squared level, and so on. So we can do it not only at the level of the Lubin-Tate deformation space, but also for the full open modular curve. Okay, open in the sense that I do not consider the cusps. And let y infinity, so yn would denote the modular curve of level p to the n over qp, and maybe some tame level if you want. And y infinity will be the scheme which is the inverse limit of this. That's a perfectly good scheme. Projective limits exist in schemes. It's not a finite type, but it's a perfectly good scheme. A point of that scheme in C is by definition almost an elliptic curve, maybe with tame level, but also equipped with a full trivialization of its p-adic Tate module. And as before, we can get a map pi Hodge-Tate in this case from such a point to a point in P1C. Okay, by the same recipe. It didn't, okay, we're not using anything more than is available here. Okay, so here's a theorem. The map now from y infinity C, from the full modular curve at the infinite level, to P1C is surjective. If you look at the QP point of P1C, remember that P1C is canonically P1. So it makes sense actually to look at QP points of it. Okay, it's not just up to change of variables over C, it's canonically P1. So if you look at the preimage of a QP point, you get, of course, many triples, it's not one-to-one, but they're all in the ordinary part of y infinity. The elliptic curve E will have good ordinary reduction or bad, but since it's over algebraically closed field, it will be a split multiplicative. The inverse image of the complement of P1QP, which is the Drinfeld upper half plane, is the supersingular points, is the points where E has good supersingular reduction. Now, this is really surprising, really an anomaly, because at finite levels, we usually think of the ordinary part as being big and the supersingular part as being small. Okay, the reduction of the supersingular part at each finite level is just a finite number of points. Okay, so without talking about the reduction, it's a finite number of residue disks in the rigid analytic picture. And the remaining part is a big aphenoid, or union of aphenoids, that is fat. So you would think that when you go to the limit, this picture that we have in mind of what's small and what's big, what's meager and what's fat, would remain the same. However, the fat set of this ordinary points gets mapped via the pi Hodge-Tate. That was a little bit early, right? Okay, gets mapped via pi Hodge-Tate to the meager set, which is just P1QP, which is like a counter set, rigid analytically. On the other hand, the supersingular locus at the infinite level fills up the whole complement, the whole. So maybe you will talk about it today when you talk about the perfectoidness of this thing. Now, this actually can be explained. This is a point that can be explained and proved without much effort. If E is ordinary, what does it mean that the Hodge-Tate map sends us to a QP point? It means that this line in TP tensor C really is defined over QP. So you can really detect it already in the Tate module. But you know how to detect a line in the Tate module. It's so to speak the line corresponding to the kernel of reduction or the canonical subgroup or whatever name you give it. Okay, so there is such a line, and it's easy to check that it spans the kernel of alpha G. Well, in this case, the kernel of alpha G is one-dimensional in a two-dimensional thing. So this proves really one direction, that the Hodge-Tate map takes an ordinary elliptic curve to P1QP. In the converse direction, let me only prove it when E is defined over some discrete valuation field K. And if you know that E is defined over a complete K, so finite extension of W1 over P, and you know that the Hodge-Tate map lands in P1QP, then you know that the action of the Galois group, because you have this line inside, is potentially reducible, diagonalizable. Okay, so it has the familiar shape associated with ordinary representations of the local Galois group, and you conclude that E is ordinary. Now, in general, the image of pi Hodge-Tate for h bigger than 2, okay, so going back, what have we seen? On the global picture, pi Hodge-Tate is surjective. But if we now focus once again only on the supersingular disk, the image, according to this, is just the Drinfeld upper half plane. And this is, in fact, something pretty general. In the Lubin-Tate moduli problem, the Hodge-Tate map maps M infinity onto the Drinfeld p-adic symmetric domain. And let me remind you, if you have not seen it, at least on the level of C points, this is what you get from the C points of projective space of dimension h-1 when you delete all the QP rational hyperplanes. So not just QP rational points, as we did when h was 2, but in general you must delete all the QP rational hyperplanes. This is some rigid analytic open set on which GLHQP acts and is very interesting. And as we saw before, pi Grothendieck-Messing induced an isomorphism between M infinity over GLHQP to, in that case, it was the projective space, and here pi Hodge-Tate, which is completely different, induces an isomorphism between M infinity rigid analytically over D star to the Drinfeld space. So let me very quickly, in the remaining 5 minutes, go over what happens when you add PEL structure. So you know that in the study of Shimura varieties, it's not enough to consider the Siegel case. Well, the Siegel case actually has polarization in it already, but often you want endomorphisms. E is for endomorphisms, L is for level. And we will actually ignore P and L, the polarization and the level, and let's focus only on the endomorphisms. So we now enrich our situation by considering, in addition to the input that we had before, a semi-simple algebra B over QP with a maximal order OB that is embedded in the endomorphism algebra of our given H0. So you do not consider H0 naked, but with an action of some interesting, maybe division ring or maximal order in the division ring. By functoriality, this B will act on the rational Dieudonné module or the crystal evaluated W in a way that commutes with Frobenius and will stabilize the lattice given by the crystal itself, not the rational crystal. So what Rapoport and Zink do in this situation, they also fix some, they call this model Dieudonné module V, and they fix a decomposition of it. In this case, Lubin-Tate case, it would be into subspaces of dimension D and H minus D, so that V0 maps isomorphically or intersection with lambda with this lattice maps isomorphically onto the Lie algebra of H0, and V1 reduces modulo P to omega H0. Okay, so they somehow lift on the level. So that's an arbitrary splitting that you can do over in this linear algebraic or semi-algebraic, semi-linear context of the situation mod P. And now you enrich also the deformation functor by considering not only G iota, but G iota and lambda. Lambda refers to the polarization, which we have not added. It can be added in general. But the important thing is that the G now should be not only a p-divisible group over S, but endowed with a compatible action of OB that is compatible with the iota and with the action that we gave on H0. And in addition, we want to add a condition that is empty when OB is just ZP, and we want to add some signature condition telling you how the elements of OB behave when they act on the Lie algebra. So you have a model for this action given by this V0. Remember, V0 was this arbitrary splitting of V, but that reduced to the Hodge filtration mod P. So anyhow, it's of the dimension of the Lie algebra, and it maps to the Lie algebra mod P, so it makes sense to ask that the way A acts on the Lie algebra of G is the same way that in this model vector space A acted on V0 in terms of determinants. And the theorem is that this functor is again representable by a formal scheme, same result as before. I copied it, copy-paste. And our goal is, can I take 2 more minutes? Or yeah, then I'll really round up everything now and finish with this topic. Our goal now is to look at the Greenfield p-adic symmetric domain, the symmetric domain that we obtained as the image of the Hodge-Tate period map, is a Moduli space for such a deformation problem. So this is in fact due to Greenfield, which was long before Rapoport and Zink, 20 years before Rapoport and Zink. And the situation is this: we take for B our familiar, right, this B that figured out in this generalization, our familiar division algebra of invariant 1 over H. And now we make a definition of what is a special formal OD module. So now it's a formal group of height H squared and dimension H. So Contrast it with the Lubin-Tate case where the height was h and the dimension was 1. Now the height is h squared and the dimension is h. But the bonus is that you can equip it now with a very interesting action of OD, of the maximal order of that division algebra. And the condition is that on the ring of integers of the unramified extension of degree h of QP, which is of course embedded inside this OD, you get on the Lie algebra, okay, which is of dimension h, basically h different characters, basically the regular representation. This is what's hidden in the word special. So a formal OD module would just be something like this, equipped with an action of OD via endomorphisms, and it's special if this extra condition is met. So here is a standard example. Let's denote now by, boldface H0, the previous H0 that we had in the Lubin-Tate case. Okay, so this was the unique formal p-divisible group of dimension 1 and height h over fp bar. Okay, so it had, over fp bar, it had an OD action. Okay, here we want the OD action in the Moduli space to persist for all the deformations. There, we're lucky to have this OD action on the thing over fp bar, not over deformations, as you know. And you take h copies of the same h0, so of course the height becomes now h squared rather than h, and the dimension h rather than 1. And to make it a special module, you twist on each of the copies the action of OD by the corresponding power of Frobenius. And this is our model H0. And you can write down what the M0 would be, and the V with Frobenius, and with the D structure. So the V would look like D tensor W. It would have the D action by D acting on the left. Linearly, it would have Frobenius by pi coming from D. Pi, remember, is an element of D acting on the right. So this right action commutes with the left action of D. But of course, this should be a semilinear action. So you should really write pi acting on the right tensor sigma. And finally, the result of Drinfeld, with which I end, is that this formal scheme is, that we discussed, is in fact the formal scheme that represents, I'm skipping a step. The Drinfeld upper half space that we described before on the level of C points has an underlying formal scheme structure, which is the formal scheme representing the Drinfeld deformation factor. So I write it in calligraphic X for the formal scheme and Fraktur X for the rigid analytic space. But at this level of generality at which we're doing things, you should think of them as being the same thing. So this I only wanted to add at the end because we will need it if we discuss at the very end the isomorphism between the Lubin-Tate tower and the Drinfeld tower. Okay, so thank you very much.